The last couple of weeks we've been looking at the web tier of Java Enterprise Edition and thinking about how those principles apply generally to enterprise applications. Today we're going to take a look at the business tier, at least begin to take a look, and focusing on session beans. The idea of session beans is that we will write our business logic. The business rules will be enforced in the business logic inside a set of session beans. Why we would want to do that is because we're dealing with enterprise applications. Therefore, there are going to be a lot of different applications all wanting to use the same kind of logic. And we need to make that logic available. One way that we can do that is to write a set of services. So session beans are essentially a set of services. And that allows us then to write these multi-tiered applications that will deliver scalability, accessibility, and manageability. As I've mentioned in a previous lecture, the platform that we're using, Java Enterprise Edition, provides a standard set of system services that will allow us then to solve very easily, because they've done it for us in the framework, difficult problems such as security and transaction management. We'll talk a little bit about transaction management a bit later on in this lecture. And that allows the developer to focus on business and presentation logic without having to worry too much about the other kinds of logic in MVC. We consider Java Enterprise Edition applications to be three-tier. We've already seen that enterprise applications typically will have to have multiple tiers because they will have large volumes of requests, and therefore one piece of code, one class, one object will not be able to deal with all the requests that come in. And so we'll need to consider concepts such as distribution or clustering. We'll talk more about that in a few weeks. Also, because we're in an enterprise context, there are going to be many machines. We're not in a situation where one computer can run the entire office. In fact, with an enterprise, it's very possible that the offices, multiple offices, are going to be scattered at least over a nation and possibly over the globe. And so one computer will not do everything. We're going to have client machines that are running applications, presenting information. Those applications might be bespoke applications written maybe in Java, for example, with a desktop application. They might be web applications where the web browser is executing on the client machine. These are all talking to at least one server machine and possibly multiple server machines, and we'll have to think about that in terms of distribution or clustering. And very often the database or legacy information systems are going to be on different computers. So we get a system that looks a bit like this. Multiple machines with different components on the application being distributed amongst those machines. One of the things that might be missing from this diagram would be about here and web services. You've already seen a little bit about web services, probably read about it, maybe even used them in your placement. And later on in this module, we'll think a bit about web services. They sit here right on that web tier, ready for interaction with the business tier. One of the reasons why we want to have this separation of responsibilities in this way is because of the non-homogeneous clients that we would be dealing with. And if we've got lots of different types of client, at some point, for efficiency of development, we will want to have common functionality available to all those clients. And that's why we want to develop these components that offer services that then can be used by the different types of client. And Enterprise Java Beans, EJB, provide some of that service. So an Enterprise Bean, Enterprise Java Bean, is a server-side component. It encapsulates the business logic of an application. In other words, it encodes the business rules for that application. As I mentioned a few moments ago, it simplifies the development of large distributed applications, especially where we've got multiple types of client, so that there is this point where eventually all those clients will come into that common service area. And these enterprise beans provide that common service. It also means that when developing the presentation logic, we can build thin clients. In other words, clients that only focus on presentation of data, and that data has already been processed within the business tier of the application. So we have thin clients with a rich server-side application. There are two types of enterprise Java beans, session and message-driven. Today we're going to talk only about session beans. We'll focus on message-driven beans at another time. The session beans provide enterprise functionality as services. These are typically synchronous communications, whereas message-driven beans enable asynchronous communication between different components within an application. Asynchronous meaning that the message can be sent, maybe a request that's sent for some information, and then the sender of that message will just continue processing, and eventually, possibly days later, a response will come back. And when that response is returned, the sender of the request will process the response. Synchronous is very much like a method call that you're used to dealing with. The caller of the method will block and stop processing until the response comes back from the message that it called. And that's what's going to happen here. The session beans will have methods that are called by other components. Those components will block and wait for a response from the methods in those session beans. Session beans can represent transient conversations with a client. Transient means that it is not going to be a permanent conversation, although in some situations we can make it a more prolonged transient transaction. And it's important to realize that a session bean is not persistent. It does not exist over a very long period, which means then that when we build these session beans, we have to remember that they won't exist for a long period, and we've got no guarantee that when I'm talking to a particular client, that my very next request will come from the same client. It might be from a different client. And a client, when talking to a session bean, might have no guarantee at all that the next time it sends a request, that it'll talk to exactly the same instance of that bean. If we do want to persist information, in other words, store information over a period of time, then we want to use a database. What we're going to use in our enterprise applications is a set of entity classes, and we will talk about those on another occasion. Essentially, those entity classes will represent rows of data in the database, and when we interact with those entity classes, or at least objects of those entity classes, then we'll be causing changes to occur in the database. But we won't have to write the code that updates the database. That will happen automatically. Because these session beans are held in the business tier, it might be that that business tier is on the same computer as the client components, or it might be on a different computer. And more importantly, it's not so much whether it's on the same computer or not, but whether it's operating in the same Java virtual machine or not. So depending on what we've got, we will have to choose a mechanism whereby we can communicate with these session beans. So we're going to expose the methods of those beans as interfaces. And those interfaces can be local, remote, or indeed a web service. If they're local, it means that the two components are in the same Java virtual machine. If they're remote, it means that they're in different virtual machines. And web services, well, we know a little bit about web services and what they do for us. So using those interfaces and the methods that are exposed in those interfaces, we are able to invoke the methods of that session bean from the clients. And that means that the client, as I mentioned a few moments ago, can be thin. In other words, it's not going to have a lot of processing within the client. It's going to have instead a connection to the session bean, call some methods in that session bean, and the bean will do all the processing and simply return the results to the client so that the client can then present that information. We have three types of session bean: stateless, stateful, and Singleton, which are summarized here. Let's start at the bottom with Singleton. This is, as you would expect from the name, a bean that has exactly one instance per application. And it will come into existence and exist for the entire life cycle of the application. Now, the implication of this is that that one instance will be used by all components that want to use it. So there is sharing going on, a lot of sharing. So we can have potentially many threads all executing inside that one singleton at the same time. We might also find that data is being stored in those singletons, and therefore the data is being shared across different requests. That means that there is no privacy of data in a singleton, in the sense that a request from client number 1 and a request from client number 2, if they are both using the singleton, they will be accessing exactly the same data that is stored within that singleton. So for example, if it's a banking application, you do not want to make the login information and the account details data that's held within a singleton, because it means that client 1 can see all the information that's just been put in there for client 2, and that's not desirable, of course. Let's consider stateful. Stateful is a situation where a given session bean instance is dedicated to a conversation with a single client. It means that the client will send multiple requests to that stateful session bean and will interact with exactly the same instance every time. Because of that, it means that data from one request can then be stored in that stateful session bean so that it can be used by other requests from the same client at a later time. To preserve privacy between clients, a given instance of a stateful session bean will only be used by one client. It will not be shared between clients, but it will be shared between requests from the same client. Sometimes that bean will need to be written to storage so that the concept of persistence and maintaining state between requests can be facilitated. For example, if between requests the server has to shut down, then all stateful session beans will be written to secondary memory. When the server restarts, those stateful session beans will be reinstated in primary memory. Because the state for that client is held within the stateful session bean, if the client removes that bean, the state for that client will be lost. And when a subsequent request from the same client comes in, then it will be as if this were the first request from the client, because previous state has been lost. Now this can be a little bit expensive in terms of processing, because if you've got 1,000 clients all making use of stateful session beans, then they will all have their own instance of that stateful session bean. And if they're all making use of, let's say, 2 or 3 or 4 different session beans, all of them stateful, and there's 1,000 clients, then you're going to have up to 4,000 instances of session beans being held in primary memory for that interaction. That can be quite expensive in terms of memory and also in terms of managing those instances. It would also make it much more likely that those instances will have their information written to storage, because it might be that the server's memory cannot hold all of those instances in memory at the same time. And so it will have to write to secondary storage those that haven't been used for a little bit so that it can process the most immediate requests. And then when a request comes in for that session bean that's just been written to storage, then we'll have to bring it back from storage so that the request can be processed. That writing to storage and reinstating from storage is going to take time, and therefore will affect response times from the client's perspective. Because of these problems, it's much more desirable, wherever possible, to use a stateless session bean, which is at the top of the screen here. The stateless session bean does not maintain a conversational state. In other words, a client will send in a request, that request will hit the session bean, an instance will be used, and then the instance will immediately forget everything that it's had to do with that client. It just processes that one request and then forgets it. No state is maintained. And therefore, when a second request comes in from the same client, if it goes to the same instance of that stateless session bean, the stateless session bean will have no concept whatsoever of having previously processed any request from that client. Because a stateless session bean will only deal with one request at a time and then just forget any state that it had, it means that that one instance can be used to process requests from many clients. without there being any risk of leakage of data from one client to another. Data privacy is maintained. But of course, if you've got 1,000 clients and you've only got one instance of that stateless session bean, not only is that session bean going to be very slow in processing, but it's also going to be very busy. Therefore, to manage the workload from a large number of clients, what will probably happen is that that stateless session bean will be instantiated many times. And each request will be sent to an available stateless session bean. But it might not be the same stateless session bean that the previous request from that client was sent to. And that's another reason for not maintaining state in a stateless session bean, because one request from client 1 will go to one instance, and then another request could very well go to a different instance. These are never written to secondary storage. There's no need to. There's no state being maintained. Therefore, offers better performance. We can also use these if we want to expose the services of that stateless session bean as a web service. So if we want to choose between stateless or stateful, we've got to think a little bit about some conditions. Remember, stateless session beans, use them if you don't need to maintain state. On the other hand, if the bean's state represents the interaction between the bean and a specific client, i.e. we're maintaining state between requests from a given client, then we would definitely want to use a stateful session bean. And there are other conditions on screen at the moment that, if true, would mean that we would want to use a stateful session bean. Now, the life cycle of a stateful session bean has basically two states, ready and passive. When the EJB container gets a request for a stateful session bean, it will, first of all, create an instance of that stateful session bean, then do all the dependency injection. In other words, any resources that are required will be instantiated and brought into the scope of this session bean. The next thing that happens is that a method that has been annotated post-construct will then be called. That allows us to do any processing that is to occur before the bean becomes available for use by the clients. And then EJB create is called. When that's done, it is considered to be in the ready state. It can accept business method calls. The clients can use it. Now, it might be that the stateful session bean needs to go into passive mode. In other words, it hasn't been used for a while and it needs to be moved into the background. And so the EJB container will call the method that has been annotated with pre-passivate. So for example, if when moving into the ready state, the post-construct method created a connection to a database. It shouldn't do that in the environments we're going to be using, but if it did, that connection to the database probably ought to be closed before this session bean moves into passive mode. And that would be something you could do in the method that has been annotated as pre-passivate. But of course, having gone into the passive state, when it comes back into the ready state, it needs to be in the same state as it was before going into passive mode. And therefore that you will have to write a method that has been annotated post-activate, in which you will do things like restore the state that you put into sleep mode, as it were, when you went into passive state. You might want to reconnect to the database. At some point, the stateful session bean will no longer need to be used for a particular client. And when that condition has been determined to be satisfied, then the EJB container will have to destroy that instance because it's holding state for a particular client. When that client no longer needs it, that will have to be destroyed. So two things happen. One is that the client will invoke the method that has been annotated at remove, which will be the signal to say, remove this stateful bean, I don't need it anymore. And then the EJB container will call the method that has been marked pre-destroy. It might close the connection to a database. And then the instance of that session bean is ready to be collected by the garbage collector. So the important thing to note here is that the client initiates the lifecycle by obtaining a reference to a stateful session bean. That's all it needs to do. There's nothing special. It just needs to obtain a reference. And that's part of what happens, for example, with the dependency injection right at the beginning of that lifecycle. And it's the EJB container that controls the calling of these lifecycle methods, pre-passivate and post-activate. So a stateless session bean can be used to improve performance because we're not having to maintain multiple instances across many calls from the same client. And therefore, it's got a much simpler life cycle. It's either ready or it isn't. Moving into the ready state will require some dependency injection. In other words, let's obtain the resources that we need, and calling a method called postConstruct. Because it is a stateless session bean, there's no concept of becoming passive. So there's no need for a pre-passivate and a post-activate method. So it just stays ready all the time. Clients can send in their requests, call the methods from that. The methods process the requests and just wait for the next request to come from, well, absolutely any other client. It doesn't have to be the same client as before. Eventually, the EJB container will decide it's time to destroy this instance and will call the method that has been annotated with pre-destroy. The point being made here then is that because the EJB does not have to continually create and destroy instances of a stateless session bean, then it can do something like maintain a pool of beans that it can share across all the various clients. We mentioned the Singleton session bean earlier on. Just a reminder, these beans will be shared across all clients in the application. Therefore, be very careful about the data you put in those Singleton session beans. They will be shared across all clients. We can also do things like perform tasks on application startup and shut down within these Singleton session beans. And with a little bit of care, we can also expose these as web services. But remember that they are used across all clients. So please be careful about the data you put in them. Again, a very simple life cycle, much like the stateless session bean. Dependency injection, post-construct, then I'm ready. That bean will come into existence when first it is requested, unless it has been annotated with @startup, in which case it will come into existence when the application comes into existence. And in those kinds of Singleton session beans, the ones marked with startup, in there you can do tasks that need to be done for the entire application when the application first begins. Like with the other session beans, in the ready state it can receive calls to its business methods, and then eventually it will be destroyed, typically right at the end of the application's life cycle. Now this means that we're able to build applications that are scalable, and this is one of the design principles for enterprise applications. We need to build applications that are scalable, that we can make bigger, or as numbers of users increase, we can give all those users the same level of performance, no matter how many there are. So we can scale up the amount of processing power that is necessary to handle those requests from those increased number of users. And that means we're going to have potentially different models of distribution or clustering. As I said earlier, we will talk about that in another lecture. If you are scattering components across different machines, that has to be completely transparent to the client. As far as the client is concerned, it's just asking for a resource, and it will be up to the EJB container to determine where that resource is and make it available to the client. It must not be the responsibility of the client to work out, oh, it's on server 1 today, but yesterday it was on server 2. That should be entirely transparent to the client. We also want to ensure data integrity, and we will use transactions for that purpose. You might have come across transactions in working with databases. We can implement the same kind of concept in our enterprise applications, and I'll talk quite a bit about that in a few minutes. The other thing is, because we've got a variety of clients, we don't want to have a difficult way of locating the enterprise beans that we want to use in those clients. Therefore, we need some interfaces that will make this much easier. I said earlier that we've got local and remote as two different types of interface. Remember that the local interface is used when the client and the resource that it is using, in this case a session bean, are deployed in the same Java virtual machine. If they are in different virtual machines, then you will need to make use of the remote interface. Which to use will depend on a few things: the kind of coupling, the kind of client, the distribution model you've got, and the performance that you want. If you have two session beans that depend on each other, for example, session bean 1 is going to call session bean 2, then those beans become tightly coupled. Therefore, you will probably want them to be on the same virtual machine, because that will make performance that little bit better. Therefore, you would probably want to use a local interface between those two. The other thing is that they fit together as a logical unit. They belong together. If you move one of them to another machine, then the other ought to go with it, because otherwise you're going to start degrading performance, because there's going to be that additional overhead of communication between different computers. If you're using application clients, now an application client is an application on a different machine that is talking to the server. That means you're going to have to use remote access. When you're dealing with enterprise applications, if you've written an application client, it is inevitable that it's going to be on a different machine from the server, and therefore you're going to have to use a remote interface. If you're distributing your components across different machines, you will need to make use of the remote interface, whereas if they are clustered on the same virtual machine, then you could use the local interface. And the idea of performance between the two really hinges around factors such as network latency. It's very likely that remote calls are going to be slower than local calls. The reason being that inside the same virtual machine, it will essentially be a method call from one component to another. Method calls are very quick. Whereas an invocation from one virtual machine to another is likely to make use of the network, and we've got no control over the network and the traffic on the network and the routers in the network and the path that will be taken from one computer to another when sending a request for a service from another session being on a different computer. Therefore, there's going to be some kind of delay. That's the latency in the network. That delay is likely to be much longer than the delay between a local method call. So performance between remote components is going to be slower on average than calls between local components. Now, of course, these are fairly general statements, and you will have to look at your individual operating environments and think about what you want to do. But the point is that you want to make those response times as quick as possible. And so you're going to have to make decisions and weigh in the balance the advantages of using local method calls instead of remote method calls, and weigh that against the restrictions that local places on you in terms of distribution. Because if you've got local components, then they've got to sit together on the same machine. And if you want to distribute, that's going to determine just how many components can be moved onto a different machine at any one time. Let's talk a little bit about transactions now. The idea of a transaction is that it becomes an event, in this case a change event, that is atomic. It must entirely happen or not happen at all. Think about a bank transfer. You're going to transfer some money into someone else's account. There are two operations involved. Withdraw money from your account, deposit money in the other person's account. Two separate operations, but they must be considered as a whole. You don't want that to be half complete. You don't want the money to come out of your account and just vanish. You want it to go back into the other person's account. So both the withdrawal and the deposit must happen, or if one of them doesn't, then the other can't. That's the idea of this transaction. It enforces the integrity of that operation. It will ensure that it completes fully or will be undone and not occur at all. Transactions provide this mechanism then to bundle up a set of operations into what we call an atomic execution unit. And this is really important when you're using distributed enterprise applications. You've got components on different machines, and it might be that you're maintaining some state on different computers. And if one of the computers finds an error when other computers have already done some processing for a particular request, you don't want the situation of the first machine saying, "Oh, I've got an error, I'll stop processing," and the other machine saying, "Oh, I didn't know about that error, I'll just carry on." You now get an inconsistent state between two parts of your application. That is not desirable. If you bundle up all these operations in a transaction, then you can begin the transaction. The first machine can do its processing, second machine can do its processing. If the first machine finds a problem, then it will say, "Stop, and the transaction is undone, and that means that both machines will undo the processing that they have done thus far. And the system, the entire application, is left in exactly the same state as it was before the transaction began. And that is a very useful mechanism when dealing with distributed applications. So a transaction should have ACID properties: atomicity, consistency, isolation, and durability. Atomicity we've just talked about. Either it happens or it doesn't. There's no concept of it kind of happens or it happens a little bit. It's either all or nothing. Consistency, well, that's what I was just talking about with the two different machines processing the same request. Everything must be left in a consistent state. Either the operation has occurred, in which case state has changed, or the operation began and then was aborted, in which case the state is left consistent with how things were before the attempted operation. Isolation means that concurrent transactions must be isolated from the updates of other incomplete transactions. So when a transaction begins and we're mid-processing, no other transaction can see what's going on in terms of state until that transaction has completed or rolled back. And when a transaction commits, then its effects will be permanent, at least until the next transaction comes in and makes a change of state. We can use transactions with any of the EJBs. When we're dealing with bean managed transactions, then we, the developer, have to write all the code that manually handles the transactions. A much easier way is for us to make use of container managed transactions, in which case the EJB container will use annotations to begin and end transactions and will apply different strategies depending upon the kind of transaction value that has been selected. So we can say, look, I want to annotate a class with a particular transaction attribute. And that means all the methods in that class will have that particular transaction attribute. Or we could say, let's just focus on one or two key methods. And those key methods can then be annotated with the attribute. So the values of the transaction attribute are several. For example, if we say that the transaction attribute is required, we must operate inside a transaction when executing that method. So if the client is already using a transaction, then this method will use that client's transaction and operate within the context of that client's transaction. On the other hand, if the client was not running a transaction, because a transaction is required in this particular case, then a transaction will begin and will not finish until this method has finished its execution. Requires new is a slightly different scenario. If the client is already running a transaction, then that transaction is suspended and we start a brand new transaction, call the EJB's method within the context of that new transaction, and then when this method has finished executing, that transaction terminates and then resume the client's transaction. And if the client doesn't have a transaction at the moment, then a new one will be created anyway. Mandatory means that if the client is running a transaction already, then we will use that client's transaction. Otherwise, we will throw a transaction required exception. In this scenario, a new transaction is not created. Not supported means that if the client is running a transaction, then that transaction will be suspended. The EJB method will run to completion outside of the context of a transaction. And then the client's transaction will resume. If the client doesn't already have a transaction, that's fine. Then we don't need one for this type of attribute. And so that method will just run. And then we've got supports. If the client is running a transaction, the method will execute within that client's transaction. If there isn't one, it'll just operate anyway. So it's saying here that a transaction could be used, but it's not mandatory. Probably desirable. But if there isn't one, that's fine, I'll just keep on executing. Be cautious with that one. And then never says that if the client is already running a transaction, then a remote exception will be thrown. This particular annotation means that I must never use a transaction when executing. If there is no transaction already running when this particular method is called, that's fine. And so the method will execute. So those are the various attributes for transactions, and the container will handle all of that. Just by way of introduction now, the Java naming and directory interface. It's a client API that will allow the enterprise developer, you and me, to name and refer to resources. We're going to use it in the context of accessing a database. We will provide that, it's called a persistence unit, that is linked to a database. We will provide it with a Java name, and it will go into a directory, and that will then become available to our application using that JNDI name. So you can see on this diagram here that the application, once a resource, these are the resources, have been registered in the JNDI server, given a name, then we can use the JNDI API to access those resources via the naming manager. We provide the JNDI name of the resource, and the naming manager will manage everything and give us access to that resource. Now here's an example of making use of that. This is in an application client. So this is probably the most complicated way of doing it, because it's in a remote Java virtual machine. And so we'd need to perform this set of code where we get hold of the naming environment by creating a new initial context object, and then calling from that object the lookup method passing in the bean name. And that will then make available to us an object that we can cast into the appropriate kind of class that we want. If we're using dependency injection, it's even easier. We'll just have an annotation to say, well, we want this kind of resource. And all the JNDI stuff in the background will happen automatically. The EJB container will take care of that for us. And we'll see examples of that over the coming weeks. If you want to read more, then you can take a look at the tutorial. It is available online as a PDF document, a very large PDF document, and it's got lots of information.